Welcome to homework.
Okay, we need to figure out how many of these methyl groups can be, equatorial or axial like, at the same time. It doesn't really matter, equatorial or axial. It's the same idea. So let me just draw the molecule in question, and then I'll kind of explain what they're getting at. Okay, methyl group on a wedge, methyl group on a hash, methyl group on a wedge, and methyl group on a hash. Okay. So the idea here is that if you've got uh, a certain relationship between carbons, like for example, we could say 1, 2, 3, right? These carbons have a 1, 3 relationship with respect to the ring. Uh, then, depending on whether one is up or down, it's possible that they could both be axial at the same time, or both be equatorial at the same time, or would not be able to be equatorial and axial at the same time, right? And we can explore that uh, more easily if we draw the chair form of this and then look at the relationships from there. So I'm going to draw a chair of this, but what I'm also going to do is just number the carbons in this ring starting at the top and going clockwise from there. 1, 2, 3, 4, 5, and 6. Okay. Okay. And then I'm going to number these. I always start with 1 being all the way at the left or all the way at the right. Okay, here we've got 3. Okay, here we've got 4, 5, and this will be 6. Okay, now let's add our methyl groups. Okay, so on carbon 1, we've got a wedge, which means it's above the ring, so it should be axial above. 2 should be axial down. Okay, 3 is a wedge, that position is axial here. 4, there's nothing, and then 5 is a hash, which in this case would be equatorial. Okay. So here's where we start to notice kind of these relationships. And that is to say, if you've got either wedge, wedge, or hash, hash, and the relationship is 1, 3, they can both be axial at the same time. Okay. So if I had a cyclohexane ring like this, right, these two groups could both be axial or both be equatorial. In fact, if one is equatorial, we know for a fact the other one is. Or if one's axial, we know for a fact the other one is. Oh, by the way, the answer to the question is 3. But that's just to get that out of the way. If you're not interested in why, the answer is 3, right? 1, 2, 3. This is axial, but we know that if we do a chair flip on this, right, then what we're going to end up with, this is 1, this is 2, 3, 4, 5, 6. Right, we're going to end up with this, and then we're going to end up with this. We're going to end up with this, and then on 5, there's going to be axial down. Okay, equatorial, equatorial, equatorial 3. Okay. Okay. But you don't need to draw the chair, right? Because the point is, if you have a 1, 3 relationship, right? It doesn't have to be 1 and 3. It could be like 4 and 6. It's just we call it a 1, 3 either way. Okay. The 1, 3 relationship between two methyl groups and they're on the same face of the ring, either both wedges or both dashes, then they will at the same time be both equatorial or both axial. The other relationship of note is a 1, 2 relationship between two groups that are on opposite faces of the ring. They'll both be axial or equatorial at the same time. Right? So 1, 2 opposite face, 1, 2 opposite face. Okay. And then finally, the other one that pops up a lot is being 1, 4 in opposite face. Okay. We don't have that here. We have 1, 4 same face. But if we have 1, 4 opposite face, if this were a wedge, for example, then these could both be equatorial and axial at the same time. 1, 4 opposite face means they'll be, if one's axial, the other will be equatorial and vice versa.